Good morning, my name is Augusto Lachini Pereira. I am from Brazil and I am a student of metallurgical engineering at the Federal University of Rio Grande do Sul, and I also work at La City, a laboratory of the steelmaking and iron making. And today I'm gonna present you the work that me and my co-workers developed at La City, and it's called Isoviscosity curves for the CSAM system in the steelmaking slags at 1500 degrees. For first of all, I would like to thank you the opportunity to make one contribution for the GTT Users Meeting 2020 as an graduate student. My work is divided into introduction, development, results and discussions, conclusions, acknowledgements, and next steps. I start the work with the question: why study the viscous behavior of the steelmaking slags? The viscous behavior, they rule the physical and chemical properties, as the gas permeability, the heat transfer, the reduction of the oxide of iron, and the height of the sulfuration. And for these reasons, for more than 6 decades, the slags viscosity are studied not just for the theoretical researcher, but also to the industrial application, with the will to improve the steam cleanliness. It is already known that the viscosity can be modified with changes in the chemical composition, with changes in the temperature, and changes in the fraction of liquid and solid slags. And to check the real influence of these three factors, it would be necessary a lot of samples to check the real influence. Then, it's well known that the high temperature viscosity measurement is costly and time consuming. Then, the thermodynamic predictions are cost effective, fast, and versatile. For thermodynamic predictions, it's possible to apply mathematical models or thermodynamic softwares, or the cooperation between the two, the mathematical equations and thermodynamic software, to obtain the viscosity value of the slags. As already known, the steelmaking slags in a high temperature present two-phase melt. It's called phase mixture, in which contain a liquid and a solid fraction. The solid particles hamper the viscosity measurement in a high temperature in the phase mixture. For this reason, the aim of the present work is apply a mathematical model and a thermodynamic software to the phase mixture and a thermodynamic software to the liquid phase to obtain their slags viscosity in a CSAM system at the temperature of 1500 degrees, and also calculate the convergence of the experimental data that I collected in the literature with the data that I calculated, in order to verify the accuracy of the convergence data of the FactSage software in the CSM system. Experimental viscosity data were collected through the published works. Here I plotted all the reference data that I collected in the literature to see better the visualization inside the ternary diagram. In blue, it shows all the modules that I utilize in this work, and red all the database that I utilize in this work. For first of all, the equilibrium and the viscosity. The equilibrium, it calculates the phase fraction, this fraction of solid and the liquid in the slag. With the viscosity, I can calculate the viscosity of the liquid part. Then, with the model of Roscoe-Einstein, I can calculate the effective viscosity of the slag. In this table below, it shows the composition rate of the all calculated slags that I calculated in this work. It is almost 6,000 of different slags that I calculated. In order to verify the convergence data between the fact sage and the reference data that I collected in the literature, for each calculated composition, it was evaluated by the difference between the measured and the calculated viscosity value. And for a performance analysis of the reference source of the viscosity calculations through the fact sage was evaluated average relative error for n measurements of viscosity. For the results of the convergence data between the data collected from the literature and the calculated with the fact sage, according with the literature, the viscosity measurement value may differ from recommended by an average of 30%. Then it can see that a lot of points it's inside the zone of the 30%, but sometimes it can see that a lot other points it's upper than this zone. For the results of the isoviscosity curves, you can see the MgO typically as a network modifier that as increase the MgO, decrease the viscosity. For the oxide of calcium, you can see in the liquid phase that as increase the oxide of calcium, decrease the viscosity. For the phase mixture has a double effect that at some point it decreases the viscosity and afterwards they start to increase the viscosity. And another thing that you can see a red in this red square is this phase that the liquid fraction was decreased. To check this phenomena, I went to phase diagram to see all the phases at equilibrium to see which one it was making this increase. Then I saw it was the milliliter phase that make this increase of the viscosity and decrease of the liquid fraction. One more constatation that I can see with the results of the isoviscosity curves is that as increase of the CO2 in the liquid phase show an expressive increase in the slag viscosity. As you can see, it's increasing the viscosity as increase the CO2. For conclusion, the convergence data between the data collected from the literature and the data calculated with the fact sage had a acceptable range of the relative error compared to the literature, up to 30%. By the analysis proposed, it was possible to see the effects of the MgO content decrease the viscosity in the liquid phase. The effect of the oxide of calcium for the phase mixture show a double effect. Initially, a reduction in the viscosity, subsequently that tends to decrease the viscosity. However, in the liquid phase tends to decrease the viscosity. For me, the fact sage showed to be a very promising for the creation for the quaternary system with the isoviscosity. Now, I want to thank you, my teammates, my co-workers and my institution, and my professor advisor, Professor Wagner and Vinicius, to everything that they helped me to create and develop this work. Thank you very much. For the next steps, I'm gonna continue this work with the several temperatures, with the new oxides, and with a new tools to visualize the effects of the viscosity. One more time, I want to thank you to be able to make one contribution for the GTT users meeting 2020. Thank you.